Hello everyone. It is a great pleasure for me to be able to present our work on a sub-100 microwatt 15 Mbps intra-body communication transceiver for body-on video sensing nodes. The transceiver uses two primary techniques to achieve state-of-the-art energy efficiencies. First, a switch capacitor-based adiabatic signaling is employed, which breaks the alpha Cp v squared f limit of power consumption in capacitive voltage mode transmitters. And second, a combinatorial pulse position modulation technique reduces the effective alpha or activity factor further to improve the energy efficiencies. Before going into the details of our techniques, I am Vaibhav Chatterjee and I am a fifth-year PhD student at Purdue University. I completed my bachelor's and master's degrees from India and had worked with Intel as a senior digital design engineer prior to joining my PhD. During the summers of 2020 and 2021, I interned with the IBM T.J. Watson Research Center, New York, and worked on cryo-CMOS implementations of quantum control and readout circuits. During my PhD, I was fortunate enough to win multiple best paper awards, including CICC 2019 and 2021, HOST 2018 and 2019, and the 3MT Award in RFIC 2020. My research interests include low power, high-speed secure circuits and systems for next-generation healthcare and body area applications. And to that end, in this year's ISSCC, we are presenting a sub-100 microwatt transceiver for body-on video sensing nodes, which can work with data rates of more than 10 Mbps. The system can have applications in several domains, including augmented reality, virtual reality, law enforcement, military, and sports. To motivate the requirements of high data rates, let's take an example of a 240p 30 fps uncompressed video, which requires a data rate of 6.91 megabytes per second. For a 360p video, this requirement becomes 13.8 Mbps. And for HD videos, it is 82.9 Mbps. With today's technologies, this could either be handled by digital compression algorithms at the video node, which consume hundreds of milliwatt when power consumption of both ADC and compression algorithms are included, or with high bandwidth traditional wireless, such as Wi-Fi, which can transmit 6 to 12 Mbps compressed HD video at 30 fps while consuming 50 to 400 milliwatts of power. In the recent years, human body communication, or HBC, has emerged as a promising low-power alternative to traditional wireless communication. And as shown in the right-hand side graph, it can offer more than 100x better energy efficiencies as compared to traditional wireless. In relevant works, it has been shown that HBC can offer sub-microwatt to few hundreds of microwatt communication through the body for data rates of a few kbps to tens of mbps. Such low power consumption, along with physical security properties, makes HBC an extremely promising future direction for energy-efficient Internet of Bodies with perpetual operation, where we envision that the Internet of Things will meet the human body to transform our lives by empowering human-machine interaction as well as collaboration. Moving on, this is the outline of today's presentation. I'll first discuss the motivation and the theoretical concepts of the implemented work, followed by the circuit level design details of our adiabatic transmitter with CPPM. Next, I'll show the measurement results and their relation with the theory. Finally, we'll compare this work with the state-of-the-art and summarize our contributions in the conclusion section. In terms of the motivation, we have already tried to establish the benefits of HBC in the sense that it is lower power than conventional wireless techniques. Additionally, it is physically secure for the electroquasi-static or EQS range of operations, where the signal is confined within the human body, which means that a malicious attacker cannot snoop into the signals from a long distance. However, there is a limitation in the form of a significant component of power consumption due to driving a large plate-to-plate capacitance in a wearable transmitter. And this plate-to-plate capacitance arises due to the presence of a signal electrode and a local ground plane in the traditional voltage mode capacitive or galvanic HBC. Usually, this capacitance is in the range of 10 to 20 picofarads and can be reduced to some extent by non-overlapping electrode design. However, if we look into the previous implementations of HBC transmitters, we see that the energy efficiencies are well over 10 picojoule per bit. when scaled to the same supply voltages and same plate-to-plate electrode capacitance of 20 picofarads. This implementation, however, can achieve 4.2 picojoule per bit efficiencies, which is a 2.5x improvement over the state of the art, with more than 10 Mbps data rates. To understand why our implementation achieves these 2.5x energy benefits, let's take a look at the simplified HBC transmitter for voltage mode capacitive communication. The plate-to-plate capacitance, CP, turns out to be the dominant source of power consumption when this is implemented in wearable form factors. The power consumption in this case is alpha CP V squared F, which leads to 10 picojoule per bit even with a broadband return to zero transmission at 0.75 volt supply. For narrowband communications, the energy efficiency is even worse. The previous solutions for this challenge can be categorized into two cases. First, we can resonate the CP capacitance with a parallel inductor. This will lead to lower power consumption, but it will introduce a bulky inductor in the design. Additionally, there would be a limitation of data rates that we'll see in the next slide. The other method of reducing the power consumption involves supply voltage scaling, as it reduces the power consumption quadratically, just like any other digital circuit. However, reducing the supply will lead to lower transmitted signals, and hence it will not be applicable for significantly lossy channels. In relation to the resonant HBC implementations, which we presented in CICC 2021, we plot the inductance required for resonance in blue in this slide on the left-hand side y-axis. The x-axis represents the carrier frequency in megahertz. The right-hand side y-axis, presented in red, represents the maximum symbol rate in MSPS, which is obtained from an analysis of the settling time of the effective RLC network. Now, if we look at the carrier frequency of around 21 megahertz, which is the IEEE 802.15.6 standard for HBC, we shall need a parallel inductance of about 3 microhenry, which is not suitable for on-chip implementations. Additionally, the maximum symbol rate that can be supported with a carrier frequency of 21 megahertz can be calculated to be only about 0.5 MSPS, which means that sending multiple Mbps data with a simple transmitter structure for lower power becomes challenging. However, for lower data rate requirements, the resonant technique works pretty well and has been shown to reduce power consumption by almost 33%. Now, as we have mentioned before, we notice that the dominant source of power consumption is the capacitor CP for voltage mode capacitive HBC. This is similar to any digital computing circuit, as opposed to wireless radio communication with a 50 ohm resistive load. Hence, we can utilize adiabatic switching. In this work, adiabatic charging and discharging is used for the first time in communication, which has been a well-known concept in the domain of computing in the past, breaking the alpha CP V squared F limit for power consumption. Now, the fundamentals of adiabatic switching is pretty simple. Instead of a square wave-based switching, which consumes a power of alpha CP V squared F, a slow linear ramp as the driver improves the power consumption by a factor of RCP over tau, where tau is the time for ramping the voltage from 0 to V. By making the tau higher than RCP, the power consumption can be reduced. One of the easier methods of implementing adiabatic switching is to convert one-step charging and discharging to n-step charging and discharging, and reuse some of the charge again in the next cycle. In the limiting scenario, when n is very high, the charging and discharging approximates the slow linear ramp, which has been shown to reduce the power consumption significantly. Using this n-step switching, the power consumption reduces to alpha CP V squared F over n in the ideal scenario. The second method to reduce power consumption in this work involved devising a custom modulation scheme called Combinatorial Pulse Position Modulation, or CPPM, which effectively reduces alpha, the activity factor for switching the CP capacitor. We'll discuss this method in detail in the next few slides, but first, I want to point out the advantages of these two methods as shown by the graph shown at the bottom. With CMOS-based switching and with on-off keying or OK modulation at 2.5 MSPS, the power consumption is 144.4 microwatts. With adiabatic switching, this is reduced to 85.7 microwatts. And with adiabatic switching with CPPM, the power consumption is further reduced to 51.9 microwatts, resulting in 64% lower power as compared to the original 144.4 microwatt power with OK-based CMOS driving. Now, coming to the theoretical details of the CPPM technique, this is a hardware-aware custom modulation technique that we developed with an aim for minimizing energy per unit information and was inspired from NASA's previous findings on energy-efficient satellite communication. This slide describes the CPPM encoding, which reduces the number of transitions per bit. 8 cycles of a 20 MHz carrier are considered as a symbol, resulting in 2.5 Mbps symbol rate, with each cycle being considered as a slot where information may be present. Slot 1 in each symbol is always filled, which is used to detect the start of the symbol. Now, 0, 1, or multiple of the remaining 7 slots can be filled based on the encoding. As an example, slot 6 is filled and is marked in green in this slide. The number of filled slots n will result in 7 Cn number of combinations, which could be used to encode multiple bits per symbol. For example, 3 filled slots out of 7 results in 35 combinations, which can encode 5 bits per symbol. Now, as shown in the figure on the left, CPPM can utilize either non-return to 0 or return to 0 signaling, and both are included in this test chip. For RZ, shown in red in the bottom right plot, the number of transitions per symbol and thereby power increases linearly with increasing n. For NRZ, shown in blue, the number of transitions first increases and then decreases due to the nature of 7Cn. As a result, the picojoule per bit for RZ increases sublinearly for n equal to 0 to 3 and superlinearly for n equal to 4 to 7, while the picojoule per bit for NRZ stay relatively constant with n. Hence, to increase the amount of information while keeping the picojoule per bit low, we chose to operate with n equal to 0 to 3. To further maximize bits per symbol, we utilize multiple combinations of n. For example, n equal to 0 and n equal to 1 together produces 8 combinations, which can be utilized to encode 3 bits, called CPPM 3-bit, while n equal to 0 and n equal to 1 separately could encode only 0 and 2 bits respectively. Using this approach, n equal to 0, n equal to 1, n equal to 2, and n equal to 3 together produces 64 combinations, which is utilized to encode 6 bits, called CPPM 6-bit. In terms of the system level and circuit level design details, the transmitter consists an on-chip data generator with a provision to accept external data, a modulator, which could be reconfigured in the CPPM mode and in OK mode, and a driver, which again can be configured in CMOS switching modes as well as adiabatic switching modes. The receiver uses a simple integrating architecture for high time domain gain. These details are summarized in the right-hand side table. A 40 MHz on-chip crystal oscillator is used to generate a 20 MHz clock at the transmitter. To generate the different phases required for n-stage adiabatic switching using a switched capacitor circuit, an 8-stage differential ring oscillator is used to generate 16 clock phases. The TX consists of a fully digital modulator and a driver with adiabatic switching, implemented using 4-step charging or discharging, which is enabled by a switch capacitor circuit. The switches turn on and turn off at appropriate times, as shown on the right-hand side, to generate the adiabatic charging and discharging waveforms. The 4 voltage levels in the final adiabatic waveform are generated by the combination of capacitors C1 to C4. Whenever a slot is filled in the CPPM encoding, or in a more general case, whenever we want a carrier cycle to charge the 20 picofarad load capacitor, the switch corresponds to S1 turns on first, followed by S2, S3, and S4, creating a 4-step charging waveform. While discharging, the switch S4 is activated first, followed by S3, S2, and S1. Finally, a reset switch is turned on to discharge the load capacitor fully. An n-step charging with n much greater than 4 will better approximate a linear ramp for adiabatic energy benefits. However, that will require 4n number of carrier phases to generate the control signals, thereby increasing the clocking power and complexity. As mentioned earlier, the TX clocking is implemented with an 8.3 microwatt 40 MHz crystal oscillator and then dividing it by 2 with a D flip-flop, which provides 2-phase injection to an 8-stage 3.1 microwatt 20 MHz differential ring oscillator for reduced phase asymmetry. The DRO generates the 16 phases for 4-step adiabatic switching. Now, it needs to be kept in mind that the CPPM RX needs to detect each slot for energy CPPM and each half slot for RZ CPPM. And hence, it uses a clock of 20 MHz for energy and 40 MHz for RZ. Thus, the frequency of the DRO needs to be adjusted for the receiver based on RZ or energy modes. And hence, the TX, RX, and clocking subsystems all run on separate supplies. In this case, we used 0.75 volts for the transmitter, 1 volt for the receiver, and adjustable supply for the clocking. The next section brings us to the measurement results of the test strip implemented in a 65 nanometer CMOS process. The overall performance is summarized in the right-hand side, showing a 4.2 picojoule per bit TX and a 4 picojoule per bit RX operation. And a demonstration of high-speed data transfer is shown here, where we can acquire continuous images or even a video from an ESP32 camera module and send it through a custom PCB with our IC for modulation. This data is passed through the human body, picked up by a serial oscilloscope, and subsequently processed and displayed. We invite you to watch our demonstration video and look forward to having an enriching feedback and discussion session. This slide shows the power consumption and picojoule per bit of the transmitter on the y-axis, while the x-axis shows different symbol rates. Both CMOS switching and adiabatic switching powers are measured, and different modulation schemes, including OOK, CPPM 6-bit, RZ, and energy are shown. As we can see from the left-hand side graph, adiabatic switching with CPPM 6-bit in energy mode achieves 2.8x lower power with respect to a CMOS driver with OOK at 2.5 Mbps. From the right-hand side graph, we notice that the same mode has 16.5x lower picojoule per bit with respect to a CMOS driver with OOK at 2.5 Mbps. Next, we show the power consumption and energy efficiency of the transmitter on the y-axis for various RZ and energy modes of CPPM. Although the power consumption keeps on increasing for both RZ and energy signaling as we move from a 3-bit encoding to 6-bit encoding, the energy efficiency numbers improve as shown by the bottom graph. CPPM 6-bit achieves 7.6 picojoule per bit in RZ mode and 3.5 picojoule per bit in energy mode without clocking. And the measured energy efficiency numbers for various CPPM modes correspond closely with the theoretical number of transitions per bit as shown on the right-hand side, which was explained earlier in the presentation. The average number of transitions per bit for CPPM 3-bit, CPPM 4-bit, CPPM 5-bit, and CPPM 6-bit are 1, 0.875, 0.75, and 0.82 respectively for energy, and 1.25, 1.22, 1.125, and 1.135 respectively for RZ, as compared to the average of 8 transitions per bit for OK and 4 transitions per bit for 16 PSK at 2.5 MSPS with a 20 MHz carrier. And the ratio of these numbers correspond closely with the energy efficiency as seen on the left-hand side. The measured stepwise charging and discharging waveforms in time domain are shown on the right-hand side, where the x-axis represents time and the y-axis shows the transmitter output. The waveforms are band limited due to the finite switch resistances driving the CP capacitor. The next slide exhibits the energy efficiency for the receiver for various modes, showing that up to 3.1 picojoule per bit energy efficiencies can be achieved with CPPM 6-bit mode, which is a 5.7x improvement over OK modulation. This is purely due to the higher number of bits packed into each symbol. Please note that these energy efficiencies are without considering the clocking power. When you consider the clocking energies, these numbers become about 4 picojoule per bit for the entire receiver. The time domain waveforms of the receiver are shown on the right-hand side, showing the TX output with adiabatic switching and reduced input at the RX due to the channel loss in the human body and the detected levels at the RX, which correspond with the TX baseband data. The bit error rate or BER for various modes are also shown as a function of the timing offset unit interval on the left-hand side figure and as a function of the input power on the right-hand side figure. As shown on the left, BER for CPPM modes is higher than OK at a particular timing offset because CPPM needs to detect each slot or cycle of the carrier correctly, while OK only needs to detect each symbol or 8x of the carrier cycle and hence has less strict timing requirements. For the same reason, as shown on the right, the sensitivity of the CPPM modes is worse than OK. Also, it should be noted that CPPM in RZ mode performs slightly worse than CPPM in NRZ mode, because the RX works at 40 MHz for CPPM in RZ mode and at 20 MHz for CPPM in NRZ mode. The sensitivity of the OK modes is found to be about -65 dBm and -52 dBm for CPPM at 2.5 MSPS and 10 to the power -3 bit error rates. There is no significant degradation due to adiabatic switching with respect to CMOS switching, as the human body works as a band-limited channel and smoothens the high-frequency components in both the output of the CMOS driver and the adiabatic driver. Finally, we compare the test chip performance with state-of-the-art wearable HBC transceivers. This work with adiabatic switching and CPPM exhibits the best energy efficiency at the transmitter, reaching 4.2 picojoule per bit for NRZ with CPPM 6 bits, which is a 2.5x improvement over reference 4 at 3x higher the data rates. The receiver energy efficiency and sensitivity are very similar to the state-of-the-art implementations. Notably, to the best of our knowledge, adiabatic switching and CPPM are shown for the first time in this work for voltage mode capacitive communication. In conclusion, we have identified the primary source of power consumption in voltage mode capacitive HBC to be very similar to digital computing circuits, which led to the use of two techniques: adiabatic switching for breaking the alpha CP V²F limit and CPPM for reducing alpha. These techniques enable us to have a 2.5x improvement in energy efficiency as compared with previous designs, which has the potential to enable high-speed applications around the body with tens of microwatt of power. With this, I thank you all for your attention, and I'm happy to take questions now. Thank you.